Next up, Matt Whitlock. Matt is an early mover for the Free State Project. Remember that was that easy round of applause earlier when I said Free State Project, right? As a software engineer, he is the lead developer and chief architect for a network security software company. As an anarcho-capitalist, I knew that was coming, that's why I paused. All right. As an anarcho-capitalist, he appreciates the capacity of Bitcoin to destroy the monopoly state, basically. He currently projects. Let me try this again. Hi, my name is Mike Salvi, and I'm here as your MC. His current projects include designing and programming a Bitcoin selling kiosk and writing an alternative but compatible implementation of the core Bitcoin protocol. Please give a warm round of applause to Matt Whitlock.
Right, so I kind of have to apologize. I'm a little thrown off here because I was expecting to have a laptop with the presenter tools and notes and stuff. Instead, I'm going to have to use my phone, and I'm going to have to look back at the screen some to make sure I'm on the right screen, and hopefully the mouse will work. Yes, good. All right, so I guess I'll give a little bit more of an intro about who I am. I'm a software engineer, and I work for a company that specializes in network security, and specifically in decentralized computational intelligence, which makes me a very good fit for Bitcoin. I know quite a bit about cryptography. I've implemented my own ECDSA implementation from scratch, all the big number math and everything in JavaScript and in C++. So I'm going to give you a more technical deep dive about how Bitcoin actually works under the hood. But please know, you don't have to really understand this in order to use Bitcoin. I heard the analogy earlier. You don't have to know how a transmission works to drive a car. So I'm going to tell you how it works, and maybe you'll get an appreciation for it, even if you don't get an understanding. I do have to make one disclaimer. I'm not a mathematician. I'm an engineer, and so if there are any mathematicians out there and I say something using the wrong term, I hope you'll forgive me. But I think elliptic curve cryptography is actually not that difficult. Anyone with a high school math education could do it. All right, so I'm going to give this in two parts, although there's not really an intermission or anything. First part I'm going to talk about is why and how does Bitcoin use cryptography, and the second part I'm going to talk about is how does the cryptography that Bitcoin uses actually work. And you might think that this is backwards. Often in school you learn the theory behind something and then you learn the application. But I don't like to learn that way because I don't really understand something if I don't know why it's important. So I'm going to tell you first why it's important, and then I'll tell you how it works. All right, so first off, what is cryptography? There's mainly two branches in cryptography. There's encryption, which we all have some understanding of how that works because we use it every day. We may not realize we're using it, but when you go on Gmail or you go on Facebook and you see that green bar at the top, HTTPS for secure, that means that site is encrypted. And what that means is when you enter your password, you enter your credit card number, that information, it cannot be intercepted by a third party. If a third party is watching the network, they're watching those packets, that data stream through the wires, they can see the bits, but they don't know what the bits mean because it just appears like random garbage to them. That's the beauty of encryption. It really started in the modern sense, taking off in World War II, communicating over the radio. That's an open medium that everyone can listen to, and we had to get messages to our troops in a way that the enemy wouldn't be able to understand. So they could see the Morse code on the wire, or on the airwaves rather, but they didn't know what it meant. So basically, encryption provides us with privacy. On an open medium, you can still send messages in a way that only you and the recipient can understand. But Bitcoin, nothing in Bitcoin is encrypted. So Bitcoin is completely clear text, open. Every transaction is public knowledge. Everyone on the network can know it. In fact, you can go on blockchain.info or blockexplorer.com, and you can put in a transaction ID, and you can see that transaction. You can see exactly where the Bitcoins went. But what you don't see, of course, is the real-world identities for the addresses that are attached to those transactions. So you can see that it came from this long string of numbers and it went to this long string of numbers, but you don't know who that is. And that's why we don't need to encrypt anything in Bitcoin, because there's no private information at risk. So we don't really need privacy. And in fact, that's one of Bitcoin's big strengths, is that it is perfectly accountable and perfectly open. The kind of cryptography that Bitcoin does use is the other branch called digital signatures. Digital signatures are not when you type your name into an agreement on a website at the bottom and it says, click here if you agree, and they make you put in your initials and they say this counts as a legal signature. That's not a digital signature. It's also not printing out a form, handwriting your signature on it, scanning it in, and emailing it to someone. The lawyers love to do that, and that's totally bogus too from a security standpoint, because that's very easily forged. No, digital signatures in cryptography are very difficult to forge, and they provide authenticity. So authenticity just means did the message originate from whom you think it came from, and they also provide integrity, which means has the message been altered by some third party while it was in transit, or is it as it was originally intended? All right, so digital signatures. Basically, to make a digital signature, you need two things. You have to have a message, which is what you want to sign. The message could be anything, any kind of data. So it could be an email or a PDF document, or if you use Ubuntu, Linux, all the software updates for that operating system are all digitally signed. That guarantees that a hacker hasn't gone in there and compromised it and put their own virus or malware on there that's going to capture your passwords. You know that at least that software has not been tampered with since whoever signed it originally, and you have to trust whoever signed it, obviously. But importantly, the message could also be a Bitcoin transaction, and that's where Bitcoin uses digital signatures. The message doesn't need to be encrypted. On the internet, it often is. When we send signed emails, they're often encrypted as well. That's if we want both integrity and privacy and authenticity. But like I said, in Bitcoin, the message isn't signed. The message is open for everyone to see. So from the message, you create a signature. And the signature is just a big, long number. It's a really big number. And it's so big that it would be impossible for someone to just guess. There would be no chance of them getting it right. And in fact, if they guessed thousands of them, millions of them a second, they would never do it. It'd be like the heat death of the universe before they actually got one that would work. It's a really long number, and it depends on the message. So if you change the message, the signature will change as well. In order to create a signature from a message, you need a key. And the key, unlike in encryption, where the key is what they call a symmetric key, meaning both parties in the transaction share the same key. So when you send an encrypted message, you encrypt it with one key, and the recipient decrypts it with the same key. So you have to agree on that beforehand. And there are also key agreement protocols that let you do that, even if you've never met them before. But the keys that we use in digital signatures are what's called asymmetric keys, which means that there's two parts to the key. There's a private key and there's a public key, and they're related. If you have the private key, you can derive the public key, but not the other way around. So the private key is something that only you have. It's stored in your Bitcoin wallet. Your Bitcoin wallet you should probably encrypt so that if someone gains your access to your computer, they can't use your private key to send your money, right? Because to send money, you need to sign the transaction. That's what guarantees that you've actually authorized that money to leave one of your addresses and go to some other address. That's how Bitcoin uses signatures. If you have the public key, you can verify that a signature is correct. You can know for certain mathematical certainty that someone who is in possession of the private key that corresponds to that public key did initiate that transaction. You can't know for certain whether it's actually the person whom you intended, because the private key, if you're not careful with it, someone could get it and they could spend your money. So this isn't a protection against fraud. It's only a protection that that some random third party hasn't attempted to spend someone else's money. Oh. Yeah. Oh, I guess I should mention the keys. The public and private keys are also really big numbers, just like the signature. In some schemes for digital signatures, like RSA, which is used very widely on websites on the internet, the private key is a pair of prime numbers, and the public key is just the product of those two numbers. And we rely on factoring really large numbers into their prime factors, being a really difficult problem. It takes a long time to do that. We're talking about numbers that are so large, it's like the number of atoms in the universe is less than that number. For elliptic curve cryptography, which is what Bitcoin uses, the private key is just a single number, and it doesn't have to be prime. It's just a random number, so they're really fast to generate. You can generate private keys for Bitcoins at millions a second on your desktop at home, which is really nice because in Bitcoin that means that you can generate basically for free as many Bitcoin addresses as you want. And they're large numbers, but they're tiny compared to like an image or a movie or something on the internet. So you can store lots and lots of them on your computer. So the great thing about Bitcoin, you can use a different address for every transaction that you can conduct with someone. So that gives you a great degree of anonymity on the Bitcoin network, because there's no way to track your spending habits or your transaction history. All right, so a transaction in Bitcoin, how does this work? Well, each transaction is basically an entry in what we call the global ledger. The global ledger is embodied in the blockchain. Like Josh gave in his presentation, that tower that we were building up floor by floor, where each floor contains the transactions for that last 10-minute period. Well, if you view the tower as a ledger where there's 3 columns, basically. There's a from, a to, and an amount. And the from and the to are big, long Bitcoin addresses that don't have any connection to real-world identities. And the amount is in Bitcoins, of course. So each transaction has inputs and outputs. The inputs are references to outputs from previous transactions. So if you want to send money to someone, you've basically got to claim as inputs on your transaction some previous outputs that were sent to you. So someone sends you money, you're the recipient of an output. Now you want to send that money to someone else, you are now the originator of that input. I don't want to get there yet. So the inputs plus the outputs in a transaction the inputs have to equal the outputs, otherwise the transaction wouldn't balance, right? So you can't send more money out than you're claiming in. But there's a limitation in Bitcoin by design that you can't claim part of an input in a transaction. You have to claim the whole thing. So if someone sends you 50 Bitcoin, and that's the only transaction you've ever received, and then you want to send 20 Bitcoin to someone else, you can't just claim 20 Bitcoin out of that 50. It's like you have a $50 bill in your wallet. You can't give someone a $20 bill. You only have a 50. So in an in-person transaction with cash, you would use change, right? You'd give them a 20 and they'd give you 30 back. Well, Bitcoin has change as well, but the recipient doesn't give it to you. You actually give it to yourself. So what you do in that situation is you claim the whole 50 Bitcoin in an input for that transaction, and then you create 2 outputs. You send 20 Bitcoin to the other person, and you send 30 Bitcoin back to yourself. So that's how the change works. And in fact, if you want your transaction to go a little faster, you can send a little bit less back to yourself. You could send $49.99 back to yourself. And then inputs does not exactly equal outputs. There's a small amount, and that's the fee. And whoever mines that, whichever miner on the network builds that floor in the tower, they get to take all those little pieces that are left over for themselves. And that's kind of like a tip. And it defrays their costs. And eventually, when we're not creating any more Bitcoins, and so there's no more reward for mining, that will be the economic incentive to keep doing this task that takes a lot of electricity and a lot of capital. Transactions with 1 input and 2 outputs are really common. They're probably the most common transaction on the Bitcoin blockchain. But of course, you can also combine inputs. So if you've received 20 Bitcoin from someone and 20 Bitcoin from someone else, you can send 40 Bitcoin, and basically you'll just be claiming 2 inputs into the transaction and sending 1 output Oh, another cool thing about Bitcoin, the change. So if you send two transactions out, one to the other person and one back to yourself, no one on the network knows which one is which. They don't know which transaction was the change and which transaction, or I'm sorry, which output was the change and which output was the money that you paid. So this is why if you go on blockchain.info and you see you look up a transaction on there, you can see the inputs and the outputs, and they make a guess at which at the amount that was actually spent. Which of the outputs was the amount trading hands and which was the change. They don't always get it right because there's no way to. It's just purely a guess. Yeah, inputs equals outputs plus fees. All right, what makes transactions secure? This is where the digital signatures come into play. So you can't just claim an input that someone else received as an output in a previous transaction. And you do this by signing it. So each Bitcoin address that you can generate, and I mentioned earlier, you create a private key. Each address is basically an abbreviated form of the public key that's associated with that private key. So in order to send money that was previously, in order to claim money that was previously sent to that address, you have to prove that you're in possession of the private key that goes with the public key. And that's what a digital signature gives. And no one else should have that private key. So if you can successfully create a signature that validates using the public key, which everyone else can see because it's public, then they all know that, yes, the transaction was actually generated by someone who has that private key, so we should trust it. So signatures in Bitcoin. Bitcoin uses a scripting language called, pretty unimaginatively, Script. Script is a stack-based language, kind of like Forth, if there's any programmers in here. That's a very old language. It's also similar to PostScript, which is the language used by a lot of laser printers, publishing, and that kind of stuff. Script has some simple operations that it can do, and then it also has some cryptographic operations that it can do. Like it can validate signatures, it can calculate hashes on data, it can compare numbers and make sure that they match. So this scripting language is what allows you to build arbitrarily complex transactions. Bitcoin is incredibly flexible in terms of the number and variety of different transaction types that you can do. So almost all Bitcoin transactions are simple. They're just send money from one person to another person. But that's certainly not the only way you can use Bitcoin. And the scripting language is great because it means you don't have to come up with a new version of the software when you want to do a new kind of transaction. It's like you don't need a new version of your web browser to run a new website, right? The website has the program in it, JavaScript and the HTML. So Bitcoin is like a web browser in that sense, in that it just runs the script. And whoever comes up with the transaction is the programmer of the script. Although you don't have to know how to program to do it, because you'll use a client, a Bitcoin wallet, a web service. They generate the script for you. You just put in the information that you need, the recipient and the terms of your agreement or whatever it is. Okay, so each input in a transaction contains two pieces of information. It contains, I'm using the word claimant, that is the sender of the transaction. Basically, you're claiming a previous output that was sent to one of your addresses. You're claiming that as input in a new transaction, and you're going to output that to someone else. So you have to sign the input, and you also have to provide your private key. And this is kind of an implementation detail of Bitcoin. We could have had Bitcoin addresses be the full public key, and then you wouldn't have needed to provide this information. But the public keys in Bitcoin are really long. I mean, you think Bitcoin addresses are long? They would easily be like, it would go like way off the screen. So we use abbreviations for the public keys that we call addresses, Bitcoin addresses. It's basically a hash that is then hex encoded. So when you actually claim an input, you can't check a signature against an abbreviated public key. You need the full one. So you have to provide the public key, and everyone who sees that transaction and wants to verify it, just make sure that the public key and the address that goes with it actually do match. And then the outputs in a transaction, in most transactions, they just contain a recipient's address. But there are other kinds of transactions too. There's something called pay-to-script hash, which was actually an improvement to the original Bitcoin protocol. that allows you to pay to an arbitrarily complex set of conditions for claiming that output in a future transaction as an input. All right, so we're now in part 2. Elliptic curves. This is the real nitty-gritty math behind how these signatures work. Elliptic curves was not created for Bitcoin. This has existed for quite a long time. I didn't look up exactly what year, but 80s, 90s. I mean, elliptic curves have been around for, that's a pretty long time in terms of software. It's a very new industry. The great thing about software, I love this industry being all the pioneers of software are still alive. Like the guy who invented C is still around, and you can email him and ask him questions. I'm sure he gets a lot of that, though, so I wouldn't recommend that. What's an elliptic curve? That's not an elliptic curve. A lot of people see elliptic and they think ellipse. It's not the same thing. An elliptic curve has an equation like this. And again, you don't have to understand the math, but try to appreciate y squared equals x cubed plus ax plus b. For different values of a and b, this is kind of not very sharp, but this is the a. So a equals -2, -1, 0, and 1. And then across this way, b is -1, 0, 1, and 2. So this is basically a graph of that function on an xy plane, just like you did in geometry in high school. So the curves look kind of funky, right? There's one bigger. So this curve has a really unique and interesting property, which is that you can define operations on points on that curve. So if you take the entire length of the curve as a set of points, there's infinitely many points on that curve. It doesn't stop there, by the way. It goes off toward infinity, up, and toward negative infinity, down. So you can define operations between points. Given 2 points on the curve, you can add them together. And that may not be immediately obvious how you do that, so I'll show you. If you draw a line that passes through the points, it will always hit the curve at one other point, a third point. And that's true, well, except in the case where you choose 2 points that are directly on top of each other. And then you get a line that goes vertically and it will not hit the curve in another place. You shouldn't choose 2 points like that. They're actually, they call it the point at infinity, which is where they say that the line intersects in that point, in that case. But if you do that, the cryptography doesn't work out. So you have to choose 2 points that are not vertically aligned. But if you do that, you can choose any 2 points anywhere on the curve, and they will hit, the line between them will hit. It may not be a point between them, it may be a point further out to either direction, but it will hit the curve at some other point. Then if you reflect that point across the x-axis, you get another point on the opposite side. This third point down here is the sum of these 2 points. And the math is ridiculous. Like I said, I'm not a mathematician, so I don't know why they decided to flip it over. I just know that you have to do that in order for it to work. You can also define subtraction in a similar way. If you took, like say you want to take this final point and you want to subtract this point, well, you'd have to subtraction is basically adding the negative, right? So to take the negative of this point, you flip it over, and so it would come down here. Then you draw a line between the negative point and this point, and it would hit over here, and then you flip it across the line, and you get that point. So subtraction works too. Multiplication is a similar thing. Multiplication, of course, you're taking 1 point, and you're adding it to itself, and you're adding it to itself again, and again, as many times as you need to do the multiplication. Obviously, you can't draw a line through one point and itself. Well, you can, but there's nowhere to go. So in math, we just take the limit as the 2 points approach each other, which gives you a line that's tangent to the curve at that point. So it's also the case that any line that's tangent to the curve at that point, at any point on that curve, will intersect the curve at another point. So that's the sum of a point in itself. All right, what's the problem with defining curves on an XY plane like this? Well, the problem is x and y are real numbers. And real numbers, there's a problem with that. There's infinitely many of them. You can keep dividing down if you have an interval 1 to 0, and you take it in half. So you have 0.5 and then 0.25 and 0.125. You can go on forever. The problem is computers don't have infinite memory. Computers they have a lot of memory, but they don't have infinite memory. And in order for this to work, because you're adding points together and you're multiplying points thousands of times, if you do any rounding at any point, no pun intended, if you do any rounding, it will not work. The errors will compound and you won't get the right answer in the end. So we have to use a different number system than the real numbers to represent our axes. This is something called finite fields, and this is kind of hard to wrap your brain around because the graph doesn't look pretty anymore. Instead, come on. Oh, I've got a graphic on. Like I said, I don't have my presentation tools here, so I've got a graphic on what an elliptic curve in a finite field looks like later. But what is a finite field? So a finite field is basically a set. A finite set. That is, it has a finite number of elements in it, as opposed to the real numbers, which have an infinite number of elements in the set of real numbers. So finite field, we often use integers because they're really fast to manipulate in computers. It's not a requirement, but in every software application of finite fields, we use integers, and typically just positive integers as well. So we'll take an example finite field, which is a set containing the integers 0 through 4 inclusive, 0, 1, 2, 3, 4. So in finite fields, we have arithmetic that we can perform on those numbers, but it's a little different than the arithmetic that you perform on real numbers. So you can add two elements of the set. That's not a minus sign, by the way. That's a bullet. So 1 plus 2 is 3. But what's 2 plus 4? Well, we would say it's 6, but 6 doesn't exist in this finite field. There's just 1, 2, 3, or 0, 1, 2, 3, and 4. So we use something called modular arithmetic. We say 2 plus 4 is 1 mod 5. And you can see that if you start at 2, you add 1, 2, 3, 4. So you wrap around. So 2 plus 1 is 4 mod 5. You can also do subtraction a similar way. You can do 3 minus 2, and you'll get 1. If you do 2 minus 3, you got to wrap around, and you'll get 4. So it makes sense, but it's not the way we typically think of math. You can also do multiplication. There's two ways to do multiplication. There's the really straightforward way. Like if you want to multiply 3 and 4, we would do it and get 12. There's no 12 in there. But if you take the remainder when you divide 12 by 5, you get 2. So 3 times 4 is 2 in this finite field. But you can also do it in a way called peasant multiplication. You can look up on Wikipedia what that is. But it's a way for computers to do that without having to calculate the full product. Because if these numbers are really big, that can take a lot of time. Multiplication is actually not a very fast operation. If you think back to high school and doing long multiplication, you thought it was annoying doing it if you had like a 4-digit number times a 3-digit number. Well, try doing it with like a 500-digit number times another 500-digit number. It takes a long time. But what about division? Well, 4 divided by 2 is 2. We know that. And that's not a problem because 4 and 2 are both in the finite field. But, come on. What's 2 divided by 3? Well, we say it's 2/3, but 2/3 isn't in that set. And what if we do modulo arithmetic on that? Well, 2/3 mod 5 is still 2/3. So that doesn't give us a number that's in the set. Well, the dirty secret of mathematics is there's no such thing as division. Division is just multiplication by a multiplicative inverse. Right? So we can find a multiplicative inverse in a finite field. Multiplicative inverse is often denoted as raised to the -1 power. So 2 times 3 to the -1 is what? Now we have to figure out how to raise a number to the -1 power in a finite field. There's a couple ways to do that. I think the battery in this mouse is dying. There's something called the extended Euclidean algorithm, which is what we often use on computers. It's been around for a while. Actually, it's been around since Euclid. He came up with the original algorithm for computing the greatest common denominator of two numbers. You may remember that. That's just like the largest factor that goes into both numbers evenly. Well, it turns out with a small modification of the algorithm that Euclid came up with for doing that, we can actually find a multiplicative inverse of a number in a finite field. There's also an interesting little thing that Pierre de Fermat came up with. We call it his little theorem. This only works if the number of elements in the finite field is prime, but when we do cryptography, we always use prime fields, so it's not a problem. What he said was, if you raise any number to the power of the order of the field, that's the number of elements in the field, minus 1, and take the modulo of the number of elements in the field, p, you'll get 1 all the time. So we can take that a step further. If we raise any number in the finite field to the order of the field minus 2, we'll get the multiplicative inverse. And you can think about that as if you just multiplied one more time the original number, you'll get 1, which is exactly the definition of multiplicative inverse. So in our example, 2 times 3, the inverse of 3, mod 5, if we take multiplicative inverse of 3, well, we can calculate that as 5 is the number of elements in the field minus 2. So what's 3 to the third power? That's 27. If we take 27 remainder when we divide by 5, we get 2. So 3 to the 3 inverse in mod 5 is 2. So we can check that. If we do 2 times 2, instead of 2 times 3 inverse, we get 4. And if we plug that back in, 2 times 3 inverse is 4. If we plug that back in to check, we can take 4 times 3, that's 12, remainder is 2. So it works. So that's how you do division in a finite field. You don't deal with fractions. So we don't have this anymore. We have that. And now it's completely lost, right? You no longer have the conceptual understanding that this is a curve because there's no points in between each of these points. These are the only points that exist on the curve in this field. This field happens to be a field of order 61. So it goes from 0 to 60. There's 61 elements on each axis, and these are the only points on the curve in that field. And if you choose any two of those points, you can do all the same math that you do in the Cartesian plane, like we did before with the line and intersecting, finding the third point, flipping it over the axis. And by the way, notice the symmetry is still here, top and bottom. If you drew an axis right along here, all the points will flip across. So the curve is still symmetric about the x-axis. So all that math still works, but you can't do it geometrically anymore. You can't draw lines on this because there's no way to conceptualize that. Okay, so Bitcoin uses a curve that the SEC, this is not the Southeastern Conference. I don't actually remember what it stands for. They publish a set, like a book of recommended curves. And the one that Bitcoin chose, that Satoshi, I guess, chose, was called SEC P256K1. And that is a finite field that has that many points on the curve. And just to give you kind of an idea of how large that number really is, yeah, so that number is somewhere between 2 to the 255th power and 2 to the 256th power. How many atoms are in the universe? Well, it's between 2 to the 259th and 2 to the 272nd. So for a conservative estimate, we could say that the number of points on the elliptic curve that Bitcoin uses, there's about 1 point per 8 atoms in the universe. So that's how many different private keys you could potentially generate in Bitcoin. That's how many addresses in Bitcoin could exist. We'll never run out. Oh, my animation didn't work on this slide. So I'll just go through it point by point, and hopefully it's not too overwhelming. This is how the actual elliptic curve digital signature algorithm works. And at this point, the math may be a little overwhelming, but it's not too bad. So if you choose K is your K is a random number. D is your private key. D is your private key. G is a point that was pre-selected on that SEC P256K1 curve. G is called the generator point, and it's fixed for that curve. But your D is not. D is your private key. It's a random number that you choose. You keep secret. No one else knows what that number is, hopefully. K is a random number that you choose for each signature that you're going to make. G is the generator point. So if you take the generator point and you multiply it by K, that is, you add it to itself K times using that math that we talked about with the line and the intersection and flipping it over, you'll get a point. You'll get another point on the curve, which is a point in space, so it's two coordinates, x and y. If you take the x coordinate and you take the remainder when you divide it by n, you get this number r. R is one part of the signature. Signature in ECDSA is two numbers. R is the x coordinate, And then Z is the message. Z is the hash of the transaction. Actually, it's a little bit simplified version of the transaction. But this is what makes the signature depend on the message, right? So Z is the message, R is this coordinate, D is your private key, and then K is a random number. So you calculate this quantity, R and S, that forms a signature. That's what you put in the transaction when you send it out to the network. That's what makes it signed. And then everyone else on the network can verify that that transaction actually did originate from someone who knows the D that corresponds to Q. Q is your public key that everyone knows. But they can't know what your D is because there's no way to determine, this is called the discrete logarithm problem. There's no way to determine what the D is given a Q. This is what I mentioned earlier. If you know the public key, you can't find the private key. But if you know the private key, you can find the public key. So if you know the private key, you can find Q. But if you know Q, you can't find D. But it turns out you don't need D in order to solve for for KG. Yeah. So this is the signature verification. This is what everyone else on the network does. They take the Z, which is the message, which they know. They take S, which you published in the transaction. They take R, which you published in the transaction. They take Q, which is your public key. That's you included that in the input to your transaction. And they take G, which is a fixed number. And they calculate this quantity, and that gives them a point. And if that point is the same as this point, i.e. if the x coordinate here equals R, which you published in the signature, you're good to go. And here's how the math actually plays out. You don't have to understand this again, but try to appreciate that for any math geeks in this room, this is like the moment of orgasm right here. This is like, this canceling out right here is the major win, because it means that you don't need to know D to verify that the R and S actually do give you KG, which is a quantity that's part of the signature. So you can cancel out the numbers that you're not allowed to know, the private key, and you can still verify that the signature works. I think that's the end. Yep.
How much more sophisticated is this than the encryption that credit card companies use to protect people's identity? Is it 10 times, 100 times, or equal to?
Credit card companies, well, they use encryption. They use symmetric encryption mostly for in their databases, their data centers. They use AES 256. They may use other encryptions as well. If they're smart, they would, because AES was approved by the NSA. So I don't know how much you can trust that. But it's a totally different kind of cryptography. So elliptic curve, like I said, is not an encryption. It's a digital signature. So this information is not held private. It's all public information in the sense that the transactions aren't hidden from view. The transactions are in plain view. The actual math involved in elliptic curves, aside from the finite field stuff, which is kind of tricky to understand, but to actually do the computations, it's not that involved at all. So the math involved in Bitcoin is simple enough that it can be done on, it can even be done on a credit card. Not a credit card like we use, but over in the UK where they have the chip inside their credit card and they have the little contact pad. The math is simple enough that those things could do it in less than a second. So it would be good enough that you could have your Bitcoin private key on your card, and you could go to a merchant. You could even make it an NFC version of this. Josh and I are actually working on this project, so maybe in a few months we'll have something to say about that. You could actually have it so that at the merchant you just tap your card on the counter and your card signs a Bitcoin transaction, and the merchant publishes it to the internet, so your card doesn't need an internet connection. So the cryptography is simple enough for even a smart card to do. But in terms of security, how difficult this is not based on factoring large numbers. So when we have quantum computers, when they start to become a reality, quantum computers, there's a problem with them for the security that we're using on the internet today, which is mostly based on what they call RSA cryptography. RSA cryptography could be defeated if it were possible to factor a large number into its prime factors in a fast manner. Quantum computers will allow us to do that eventually, but elliptic curve doesn't have that problem because you're not depending on a product of two primes. Your public key is not a product of two primes. It's a product of points on an elliptic curve, and that's a much harder problem to solve. You can't do that with quantum computers.
where do they get the original lines from? Did they sort of reverse engineer them, or I mean,
The
back
original
in
what?
Back in 1980, the original shapes for
Oh.
those elliptic curves.
Again, I'm not a mathematician, so I don't know. I don't know the theory behind why they chose elliptic curves. I do know that they form what's called a group, meaning that if you take the generator point on the curve and you multiply it a certain number of times, if you multiply that by the order of the group, which is that big long N that I had up on the board, you'll actually get all the way back to where you started. So it forms a cycle, and that's a group in math theory or in number theory. So that has implications throughout cryptography. Cryptographers love groups for that reason. Different cryptographic schemes, they're all basically based on this idea that you have a finite set of numbers, and if you perform some operation on one of them enough times, you'll get back to where you started. That's how you can decrypt something that was encrypted. It's just you don't know how many times to do it, and it's a really a large number.
Yeah, I had one question. I've heard people posting on forums and stuff saying that they've installed a wallet, generated an address, and seen that someone had already used that address on the blockchain. Is that just poor programming, or is that something that's could by chance happen through?
That sounds terrible. And if I had to guess, I would say that is due to a weakness in whatever algorithm is generating those addresses. So that's a real problem for computers. Generating random numbers is actually pretty difficult for computers to do because computers are not random machines. They're deterministic machines. If you have given two inputs and an operation on them, you'll always get the same output. You don't get a random answer. So computers can really only simulate random numbers, and that comes with a price, being that they're not truly random. And actually, if you're not careful, I mean very careful, you can write an algorithm that's particularly bad, and it will give the same quote-unquote random numbers with a much higher probability than it should. So what we typically insist on for cryptographic purposes is what we call a true random number generator. This is often a piece of hardware that you have to add to your computer, and it takes a really random source of information that the computer normally doesn't have. Maybe it has like a small sample of some radioactive material in it. It has a Geiger counter that listens for those spontaneous decays that occur with true random frequency. Or maybe it has a couple of oscillators that small variations, microscopic, like quantum level variations in temperature will cause them to vibrate at just slightly different frequencies. And so you can actually derive random numbers that way. But if you're using like a blockchain, actually I don't know, blockchain may be fine. But if you're using a client for Bitcoin that wasn't carefully written, it's possible that it doesn't have a very good random number generator in it. And if that's the case, yeah, you'd have a problem. You want your private key to really be random, and for the odds of someone else coming up with that same, choosing that same key to be one in the number of atoms in the universe.
So how do we know that this can't be hacked? How do we know if somebody has your public key, he can't just easily generate the private key?
It's a good question. And I'm sure, given the economic incentive to cracking that problem, if someone could do that, they could claim all the Bitcoin on the network for themselves, and they could send transactions from anyone's address without knowing the private key, because they could just compute it. So I think the fact that that hasn't happened yet is a pretty good indication that it's either so difficult that no human being will ever do it, or it's not possible.
Two questions. The one is the database, the wallet. What stops the database from getting poisoned, because it's replicating from everywhere and like a peer-to-peer?
Well, your wallet isn't. The blockchain is everywhere. Oh yeah, I should repeat it. So
the transaction database, what stops it from getting poisoned is the question.
The question is, if this database is replicated everywhere on the Bitcoin network, what prevents it from being poisoned? What prevents someone from corrupting it for nefarious purposes? And what prevents that is what we call hashing in cryptography. Actually, that's probably a third point that I should have put up there. Hashing is another way of checking the integrity of a message. So every block in the blockchain has a hash attached to it. And the blocks are, like Josh said, they're stacked on top of each other, so that each block contains a reference in it by a numeric reference to the block preceding it. So you wouldn't be able to change anything in the block preceding it without changing the hash of that block. It's kind of like a signature in that if you change the message, you change the message hash. So in order to corrupt the database, you would have to change a block in a way that doesn't change its hash, which we don't know how to do. That's the whole point of cryptographic hashes. And that's another problem, that if someone were able to solve that problem, if they were able to induce collisions, is what it's called, in the SHA-256 hash algorithm, then they could rewrite history in blockchain, in the Bitcoin blockchain, and that would be a real problem. However, if we start to approach that, usually these things in cryptography don't happen all at once. Someone will discover a weakness, and it makes it a little bit easier to solve, and then someone will improve upon that exploit and make it a little easier. So if we start approaching a problem where SHA-256, it looks like it's about to be compromised, Bitcoin is built in such a way that it's extensible. So we could just switch to a stronger, better, the next, we'll use SHA-3, actually, I think was just finalized by NIST, the International Standards in Technology. So we could transition to that. And the same thing with the elliptic curve. If someone were to figure out how to reverse private key back in, how to reverse a public key back into a private key, it'd probably be, again, one of those things that happens in stages. So we would see it coming. We'd see, oh no, they're getting closer. We're just going to swap out the cryptography in Bitcoin. And so then you'll have new addresses. You'll have addresses that start with some digit other than 1. The addresses now, I don't know what's going on. So it would be really easy to switch over, and it would be completely voluntary. If you don't want to do it, you could keep using the old cryptography at your own risk. Or if you do like the new cryptography, all you would have to do is take your whole balance, you take your 1,000 Bitcoins or whatever, and just send it to one of your own addresses. And it would be an address that's calculated on the new algorithm. And so that's how we would move forward.
Cool. Just for time purposes, we're going to do a discussion panel. So if you have any more questions, we'll just save them for that. That's going to be.
Sorry.
That's okay. No, it's fine. This is great questions. But
Okay. Well, that's it then. Thank you.